So in this data set, we have the marks of students in an examination and their result. Okay.
Okay.
Using the algorithms, you should be able to find out tomorrow, whenever we get new marks, we should be able to find whether the student passed or failed in the examination. So can you see any difference between the previous data sets that we have discussed to this data set?
Here the result is only to either fail or pass.
Exactly. So here the outcome is only amongst a given set of options, right? Either fail or pass, that's all. The output doesn't fall beyond that.
Yep.
This data set is like a multiple choice in an examination. The answer will be amongst those 4 options only, right?
Yep.
But earlier it's like a fill in the blank. You can write whatever you want there. That though the answer is this is only one, but you know it can fill with any value. But here it's like that multiple choice. Okay. So so this is our data set. So tell me a couple of things. Will we be able to use our regular linear regression for this?
We can use.
Okay, so let us see. The first problem that we definitely face is the result is a text value, right?
Yeah.
Linear regression cannot accept text value. In this, can you tell what is our X and what is our Y?
Marks is X and result is Y.
Very good. Marks is X and result is equal to Y. But when we calculated something, we all know that these are all the models that we discussed are all mathematical models, right?
Yeah.
So it expects Y to be a value, a number than a text value.
Okay.
So, but we have result as a text value. So the first thing that we should do is we should convert that result into a number. And at the same time, we also see that marks is also a value that can be units, tens, or hundreds, right?
Yeah.
Again, there is a variation within our marks also. So what is the technique that we can use in order to reduce that? Or
scaling.
Exactly. So in a simple way, I'm going to say updated marks is equal to marks divided by 100. Okay. If I do this, the maximum marks will get 1, minimum, if there are 0 marks, they'll get 0, and any value will will get a value between 0 to 1. Okay.
Okay. We don't use that, is it? The value minus minimum divided by
we can
max.
do that. We can do that also.
The result won't change.
The result will change obviously because based upon the minimum value here.
Yeah. In
the given data set, if minimum is 0, then it is the same. But ideally, for any other data sets, yes, it changes. Okay. But it doesn't mean that you should scale only in this order. As long as the idea is maintained, as long as the data is converted to a common scale, that is sufficient.
Okay.
So you can even devise your own techniques also. Nobody stops you from that. Basic idea is the data should be in a common scale. Okay.
Yeah.
So we converted marks into a scaled value. But the problem is still with the result, right?
Yes.
So can you think of any method where we can write result in terms of like numbers?
Can we assign value to pass and value to fail?
Very good. That technique is like we can assign some value to pass and fail. But it's not like randomly we can allocate some value. Okay. So let us see what we can do. This student already failed in the examination. I already know that, right?
Yeah.
The student already failed. I know that. So if somebody asks, what are the chances for this student to pass the examination? What do I say?
0.
0. Okay. This student passed the examination. So what are his chances for passing?
100%,
100%, which is written,
yeah.
Right? So if I rename this column result as probability of passing, okay. Can I say wherever the student has failed, will it be 0?
Yes.
And wherever the student passed, it will be 1?
Yeah.
Right?
Yeah.
And sorry, this will be...
There it is wrong, yeah.
And so on. 1, 1, 1, 1, 1, 0, 1, 1, 1, 0, so on. Okay?
Okay.
We can keep on extending this. So So simply I'll write if this is equal to fail, then 0 else 1. Okay. In this way, I can extend my values to the entire data. Now I'm going to hide these two columns. Okay. So these are our inputs.
Okay.
Okay. Our updated marks, which is scaled marks, and pass fail, which is the result. Okay. Now, so since we have some of these requirement, I mean, it satisfied some of the requirements. Okay. Now, what is our next step? What is our idea here? We have our marks like this. Okay. Across. These are our marks. If like earlier, let us try to plot a graph between marks and result. So I say marks on one axis and result on the other axis. Okay. If you see this, okay, there is some threshold limit like 40 marks, right? If it is above 40 marks, it is a pass, and below 40 marks, it is a fail. We don't know. Like somewhere 38 till 38 only we have data. 39 we do not have any data, right? We're assuming that 40 might be the threshold limit. So anything beyond 40 is like 1, and any point below 40 is like fail, right? So that can be the threshold limit. So, but here our idea is, unlike our regular linear regression, in linear regression, we have our X. We are trying to find a straight line that best passes through our data, right?
Yeah.
Such that the straight line is close to all the data points, right? If we deploy a similar technique here, in this case, what will happen? You will get some straight line.
It won't be close.
Ideally, we want a closest line, right? But this will be the line that is actually closest to. Equidistant, right? Otherwise, what happens? If you take some straight line like this, what happens? Yeah, some straight line like this. It might be closer to these, but it is farther than these points, right?
Yes.
So while calculating average, obviously this will go for it like that. Make sense?
Yeah.
So, but that is not the original idea here, okay? The idea is to create such a straight line, that divides our data into pass and fail. Agreed?
Yeah.
If I am able to create a straight line like this, okay? Some straight line like this, okay? Now I can say that anything that falls to the left of our orange line is a fail, and anything that falls to the right of the orange line is a pass. Can I tell like that?
Yeah.
So if I do that in that way, okay, if I create a line like that, then this particular line acts as something called as a decision boundary. Why decision boundary? A line can actually do wonders. A line can divide two countries. It is called line of control, right?
Yes.
Anything that falls to the left will be country A, and anything that falls to the right is country B. So that particular line, and there can be a line that divides our whole earth into northern hemisphere and southern hemisphere. That line is called equator, right?
Yeah.
So basically what is it doing? It is actually acting as a control point. Anything that is above the line is a northern hemisphere, anything that is below is a southern hemisphere, right?
Yes.
Similarly, this particular straight line is a control point here. Anything that falls to the right belongs to one part, and anything that falls to the left belongs to the other half. Clear?
Yeah.
Now our idea is to find the equation of this straight line that can divide our data into two parts. Is that clear?
Yep.
So unlike earlier, where we try to find the equation of the straight line where the distance between the data point onto that straight line is minimum. Now we don't want to create such an error function such that we are trying to calculate the distance between the data point onto that straight line. We are no more concerned about the distance, right? Agreed?
Yeah.
For example, from this particular point till the straight line, the distance is very, very high, right?
Yeah.
But it doesn't matter to me. From this point, the distance onto that straight line is very, very small. I'm still okay. My main concern is whether all my passes are towards the left of this line and all my fails are towards the, sorry, whether all my passes are towards the right of this line and all my fails are towards the left of the line or not. That's all. That is my concern. Do you agree?
Yes.
I'm nowhere concerned about the distance between the data point onto my line. I'm not very much concerned about that. As long as this particular line perfectly divides my data into parts, I'm still good, right? If I am considering the distance between the data point onto that straight line as a metric, okay, there is a problem. The problem is, imagine there is a data point here, okay? So the distance between my point onto my orange line is actually far off, right?
Yep.
And what does linear regression do? Linear regression tries to minimize, sorry, the regression always tries to minimize this distance, right? Minimize the distance between the data point onto my line. Agreed?
Yeah.
So in such case, what happens? This particular line will be shifted. This particular line will be shifted and it will create a line something like this. Yeah. Because the idea is it tries to reduce the distance between the point onto my line, right?
Right.
So if I take some point that is far off to this particular right, okay? I'm damn sure that it is actually a pass. Agreed? Imagine one person who got like, I mean, some 40 marks for practical and 100 marks completely in theoretical. 140, for example, something like that, okay? So this is 100% pass, right? But because this value is too high compared to the other data points, if we are using a regression that tries to minimize the distance between the data points onto my line, it actually creates a shift because this tries to reduce the distance between this point onto our line. Agreed? So what is happening? These data points are all being misclassified, right? Because they are to the left of the line, right?
Yeah.
And these points are also misclassified because these points are towards the right of the line, right? These are considered as pass and these are considered as fail. You see that?
Yeah.
Agreed?
Yep.
So and that is the reason why we are not very much concerned about trying to minimize the distance between the point onto the plane. But we want to create a point in such a way that, okay, distance has a negative impact, which means if the point is far away from our straight line, the error is negative. Okay?
Okay.
Let us see that. Let us see how that works. Clear?
Yeah.
Okay. So now imagine that there is sorry, I was just trying something with the trackpad. Okay. So come on. So imagine that there is one point here. Okay. There is a point here. What is this point? Is it a pass or a fail?
It's a pass.
Because if the student gets, let's say, some 117, hypothetically it is wrong, but imagine, okay?
Yeah.
So it's a pass, right?
Yeah.
Okay. So now, if our classifier says that this student passed the examination, okay? If my classification says the student passed, then what should be my error? If my classifier says that the student has passed, so my h of x is equal to 1. Agreed? Then what should be my error?
0.
Exactly. Because my model predicted it correctly, right?
Yeah.
Now, if my model says my prediction of that particular student of passing is 0.75. Okay. Now, will there be any error or not? First of all, let us see what is 0.75. What does that mean? When I say my prediction of that student passing the exam is 0.75, what does that mean?
You're 75% sure that he's passed.
Pass, which means there are
25% chance for
also,
error.
Right?
Yeah.
So there is some error associated, right?
Yes.
Let us not say how much, we'll calculate that later, but there is some error associated, right?
Yeah.
Now, let us say that h of x is equal to 0.6. Okay. Now, will there be any error?
Yeah.
Will the error be greater than this or lesser than this in this case? Compared to this error, will this error that we get here will be higher or lower?
It will be higher.
It will be higher because my prediction is actually 60% chance of passing, but 40% chance of failing, right?
Yeah.
So the probability of failing is increasing. The probability of passing is decreasing, but actually the student passed, right? So if you observe that as, okay, the data point is here, right? The data point is here, but as my probability is moving from 1 towards 0, right? My error is increasing.
Increasing.
Right?
Yeah.
So if it is 0.5, what happens?
My
probability is,
yeah,
h of x is 0.5.
So 0.5% chance of failing.
Then my error, will it increase or decrease?
It's increasing.
It's increasing. Okay. So let us say my point is here. H of x, which is the probability of passing, now became 0.3. Let's say. Okay. What happens to my error?
It's in passing, right? It's increasing.
It's increasing still, right? Because my actual y is equal to 1, which means the student passed, right? So if my y is equal to 1, if h of x is reducing, okay, my error keeps increasing.
Yeah.
Agreed?
Correct.
What if h of x is equal to 0?
Then it's 100% error.
So what will be my error?
101.
No. Why 1?
Because it's completely click. If passing is 0 and because it's all inversely proportional. If
That's
passing
right.
is 0, then
My
error
is 1. But why 1? Always remember one part that is very important for an error definition. Okay. If my predicted and actual values are equal, my error will be 0. That is the least value an error can ever get. Error function can never be negative.
Okay.
Okay. If h of x and y are equal, error will be 0.
Okay.
But whenever there is a variation, whenever h of x and y are different, the error keeps increasing. Okay. Right. There is no upper limit for an error. Error just keeps increasing as my h of x and y start becoming different. Okay. There is no bound, there is no upper bound to an error. The lower bound is 0.
0.
Okay. So in this case, you cannot tell that error will be equal to 1, which means you are giving an upper boundary to an error. Highest value my error can get is equal to 1. That's what you are telling. But error itself, in the basic definition of an error is itself, the worse the decision is or the prediction is, the higher the error. Okay. If you look at our h of x and y, y tells that the student has 100% passed the examination. But my prediction is 100% the student failed the examination. They are like two ends of the world. Right? So my error will keep increasing so much that the error will be as high as infinite.
Okay.
As my prediction goes closer and closer towards 0. Okay. As my h of x goes closer and closer towards 0, my error keeps moving towards infinity.
Okay.
Does it make sense?
Yeah.
So Similarly, let us take one point. A student has actually failed the examination. Okay. Now, what will be my value of y?
Y is the student has failed the examination.
Yes.
Y is equal to 0.
Very good. Y is equal to 0, right?
Yeah.
So if my h of x is equal to 0, what will be my error?
0.
Exactly. In this case, in the earlier case, since y is equal to 1, if h of x is equal to 0, my error goes to infinity, right?
Infinity.
But
There's
in the
no
second case, y is equal to 0. H of x is also equal to 0, then error will be equal to 0.
0.
Right?
Yeah.
Now, if my prediction is somewhere here, okay, will there be some error associated?
What is the prediction?
This one. This is my actual, but this is my prediction. Let's say my prediction h of x is equal to 0.3 or 0.3 percentage of passing, 0.7% fail chance. Okay. So my actual value is the student failed, but my prediction is there is 30% chance for the student to pass, 70% chance to fail. So will there be an error associated?
Yes.
So what happens as I move in this direction?
The error reduces.
Increases because y is equal to 0, right? As my h of x increases towards 1, error increases.
Yeah.
Y is equal to 0. If my prediction goes towards 1, which means I'm predicting that the student is passing, right? The student actually failed. But if I am predicting that the student is passing, then my error keeps on increasing. Agreed?
Yeah.
Only when the student passes, okay, and my prediction is 1, the error is 0. When the student fails and my prediction is also h of x is equal to 0, then my error is 0. Clear? Any questions on that?
No.
So I'll try to put all of this, okay? I'll try to put all of this in one. I'll try to put all of this in a, let's say, in a separate sheet, okay? Our findings. So let's do this. This doesn't go. Wait, why doesn't it go? Yeah, here you go. So now let us say that this is my actual value. Okay. My predicted value. That this is my error. Okay. Now, if I say that my actual value is equal to 1. Okay. If my predicted value also is equal to 1, what will be my error?
0.
If my actual value is 1, predicted value is 0.75. Okay. Let's say there will be some error called x1. If my actual value is 1, my predicted value is 0.5. Let's say it is x2. Okay. But in this case, we know that x2 is greater than x1. Okay.
Yeah.
Error is greater, right?
Yeah.
So if my actual value is 0, okay, my predicted value is 0, error is 0. 0, it's 0.5, let's say y1. Okay. 0, 0.75, it's y2. But in this case, y2 is greater than y1. Agreed?
Yeah.
This is 0, this is 1, this will be infinite. Make sense? In this case, it is 1, this is 0, it is clear?
Yeah.
So if it depends basically upon our actuals. Okay. If my actual is 0, prediction also should be equal to 0, then my error is 0. But if not, as my predictions go higher and higher, my error keeps on increasing. Similarly, when actual is equal to 1, if prediction is equal to 1, error will be 0. But as my predictions decrease, my error increases. Any questions?
No.
Clear?
Yeah.
Easy enough, simple enough? So what we do is we try to calculate our error when y is equal to 0 and when y is equal to 1. In these two instances, we try to calculate our error. Okay. So whenever y is equal to 1, if prediction comes smaller, error should increase, right? So the function that does is, and sorry, whenever when y is equal to 1, yes, if prediction decreases, error increases. Okay. So whenever y is equal to 1, the function is error is equal to negative log h of x. Okay. Okay. So if h of x is equal to 1, log 1 is equal to 0. Okay. This negative sign doesn't make any difference because 1 is equal to, I mean, this negative sign and minus 0 is also 0, right? So when prediction is equal to 1, actual is also equal to 1. So the error should be 0, right? So, and when error is equal to, when predicted value is 0, okay, it is log 0. Log 0 is infinite. Okay. It satisfies this, and also in values in between also. Like for example, let us say that h of x, this is the value of h of x. Okay. And this is our error. Error is equal to negative log this value, right? Now let's say this is 1. You can see error is 0.
Yes.
0.75. The error is 0.288. So let's copy this value aside. Okay. Now what happens if it becomes 0.5? Should our error increase or decrease?
Our error increase.
Increase, right? I make 0.5. What happened to our error? Did it increase or decrease?
Increasing.
Still, I make it to 0.2. What happened? What should happen to our error?
Increase.
Can you see that?
Yes.
Let's say I'm making 0.001. Further increase?
Yeah.
So you cannot define exactly at 0. Exactly at 0, you see it is undefined. But as and when it moves closer and closer towards 0, value of our error keeps increasing. Okay. And that is our error function when y is equal to 1.
Okay.
Let us see it when y is equal to 0. When y is equal to 0, our error is defined as negative log 1 minus h of x. Okay. So what does this do? Let us see that. So this is our h of x when y is equal to 0, and this is our error. Okay. So our error is equal to negative log 1 minus this value, right? So whenever h of x is equal to 0, what is our value of y error equal to? When h of x is 0, what is error? You can
1.
see on my screen.
Hello.
You can see my screen.
1 sec. Hello.
Hello, I can hear you.
Bro, I think my audio is breaking up. 1 second.